It's been a while, but I'm finally back. My baby daughter was born, I got a crib here to assemble, a not very glamorous YouTube background, in a new place, but I'm back to talk about wind loads. Did you ever open chapter 30 of ASCE 7 and instantly felt lost? Specifically on the topic of effective wind area, which is something constant throughout all those graphs in that chapter. Do you know why the smaller the pressure, actually the higher the loads? We're gonna be covering all of that, but before we do that, I have a quick announcement. I started a weekly newsletter every Saturday morning with tips, resources, community building, networking. If you want to be a part of it, make sure to sign up on the link below. Now, let's dive into components and cladding. Let's go. Now, let's truly understand effective wind area. Okay, so right off the bat, if we look for the definition of effective wind area in ASCE 7, we see that it's pretty much a combination of the gust effect factor and the exterior pressure coefficient, C sub P. At the end of the day, we're trying to find out what our pressure is, right? Our wind pressure. We have our Q sub H, which accounts for all those factors that are in chapter 26, based on the exposure classification, based on the elevation, based on topographic factors, all these things. And then we have the enclosure classification factor, or GCPI, that is to account for whether the building is open, partially open, enclosed, and then to account for specific building geometries, or the geometry around the element that you're designing, that is GCP, that factor that we're going to correlate with the effective wind area. So we have this general formula in chapter 30 that is to calculate our pressure, and then you're gonna see throughout chapter 30 all these graphs with effective wind area and then the external pressure coefficient on the y-axis. And if I'm to summarize what effective wind area is based on this definition here, we have this formula. That is the maximum of the tributary width times the span, or span over 3 times the span. That simplifies everything, and we're gonna see why this is different than tributary area. That's why it's called effective wind area. We're also gonna see all these graphs in chapter 30. We have here for walls that we have zones 5 and zone 4, the field zone. And then for the roof, because the geometry can change so much at the roof level, then we have all these different zones based on the roof type, the types of slope, and all of that, or how sloped the roof is, and all of that. Now this graph here, or this figure, I stole from the commentary, and really it talks about the envelope procedure and how they determined all of that, but I think it's a good visual for us to understand what effective wind area is actually doing. Basically, when you have a building and you have a windstorm, a wind event happening, there may be some gusts of wind and pressure or suction that will generate in random spots just because of the nature of wind. Wind is not something that's very constant and controlled. So even though, yes, the pressures will be higher at corners, it will be higher in ridges, in abrupt geometry changes, it will also be higher even in the field zone when everything is constant, just because in certain areas there may be what I would call hot spots. So we see here, for example, there may be a hot spot in this area, there may be a hot spot here, even if everything is a little bit flat, just because of the nature of wind. Therefore, if you have a small element that you're designing that has a small tributary area, even though that tributary area is small, the likelihood that a hot spot would occur for that element is high, right? Because its entire tributary area is encompassing an area of a hot spot. Therefore, we have higher GCP values for that member. Now, I just mentioned tributary area, right? So why do we have this L over 3, thing as well for effective wind area? Why not just call it effective or tributary area? Well, look at this roof here, for example. If you have load-bearing walls on either side of the roof or of the building, and then you have these trusses that are spaced at, let's say at 2 feet on center, but they're really long. Guess what? You may have a hotspot right here, but you're not going to have a hotspot encompassing the entire portion of the building. Through wind load testing, they found that the way that they're going to categorize that is by dividing them into zones based on the geometry. But because in zone 1, you may have a hotspot here, the other locations will be, let's say this is my truss right here. You may have a hotspot where I indicated here, but then lower pressures on the other areas, so it kind of averages out. Basically, if you have a long spanning member, even though that member may see a hotspot, those hotspots are smaller in nature, therefore, you don't need to be penalized in designing that entire member for that hotspot pressure, per se. So for this specific truss that we were looking at here, you'd have zones 1 prime, zone 1, and zone 2 that you would need to find the equivalent GCP value for that. You'd use your formula, see your tributary width, which let's say is 2 feet, and then the member is 60 feet long. You would have 2 times 60, that's 120, but then 60 times 60 over 3, that will be much larger than that, right? Therefore, that effective wind area is going to be greater than your tributary area. If we were to look at the graph, you would essentially find all your different values for your positive pressure, which will be the same, by the way. In this case, what really changes is not how the wind hits the building, it's how the wind exits the building per se, because it's going to pick up speed and generate suction. That's why as you move up the graph here, you're going to have different values for your different negative values of GCP to account for the negative pressure or the suction. So now that we learned the main reason why effective wind area is different than tributary area and why the smaller the effective wind area, the higher the probability that you're going to have a hot spot in that area or in that member, therefore the higher the pressures. Let's see how this pans out in an actual example. So we have an enclosed low-rise building here below. That is this image here. And we have wood studs at 16 inches on center on the exterior of this load-bearing wall, let's say. The stud height is 12 feet. Let's calculate the components and cladding wall pressures per part 1 of this figure here that I'm gonna put up in a second. For corner zone or zone 5, the roof slope is 7 degrees, and that is important to know and something that always trips people up in the PE exam or the ASCE exam, and we're gonna see here in a little bit why. And then assume that QH is 59 PSF. So we got our building. Now for us to calculate our effective wind area, we have tributary width times the span. That's 16 inches on center, 12 feet high, which is our span. That's 16 square feet. And then span times span over 3, that is 12 times 12 over 3, that's 48 square feet. So clearly here we see that if we were to consider just the effective or the tributary area, we would have a much smaller area, which would yield higher loads and penalize this member unnecessarily. Wind loads are already high in general, so let's take a break when the code allows us to take a break, right? And then when we actually use the span times span over 3, we get a higher effective wind area. So we would go then to this graph from that figure, and we'd see, okay, we're around 50. Let's move up on the graph, and then we move to the left here. So we got 2, I guess, corresponding values for zone 5, right, of our GCP coefficient. 0.9 positive and also negative 1.2. However, note that the roof slope, like I mentioned, is 7 degrees, so it's less than 10 degrees. And if we look at this highlighted note here, note 5, it states that values of GCP for walls shall be reduced by 10% when the roof slope is less or equal to 10 degrees. So I don't know why it's built that way. It's probably just how the code writers or the writers of ASCE 7. ASCE 7 is not code, by the way, but I referred to it as code because it's invoked by the code. I don't know why it was built this way, but it always trips people up in the PE exam or the SE exam because you think that you're doing everything right, you calculate your pressures, but then you forgot to reduce it by 10% because of the roof slope. It's kind of like a flat roof. And so be aware of that. Always read the footnotes in all these tables and graphs in the ASCE 7. So now we revise our GCP values, and we have positive 0.81 and negative 1.08. So if we now try to calculate our pressures, we have to pair all these different cases together, right? We have two values for our GCP in zone 5, a positive value and a negative value. But then we also have two values. It's an enclosed building, so GCPI is equal to 0.18 positive and negative 0.18. So in total, we would have 4 combinations, right? So let's play them out. So the first one is when the internal pressure here in blue is positive, and then the external pressure is also positive. The wind is hitting the building, zone 5. You can clearly see that they counteract each other, right? So they're gonna cancel out a little bit, not entirely, but they're going to reduce each other. And if we apply that within the formula, because the formula already has a negative embedded in it, so that these calculations make sense with the vector direction per se, so that the pressures that are internal pressures or pressures that are going towards the surface are always positive. Pressures that are going away from the surface are always negative. So we see here 59 PSF times 0.81 positive minus positive 0.18, we got 37.2. Now, if we look at the second case, when the internal pressure is still positive, hitting the wall from the inside, but then the exterior pressure is negative, or it's suction. Now we see that they clearly add up, and they should add up, right? When we plug the actual numbers. And lo and behold, we got negative 1.08 here. Now, the negative embedded in the formula, like I said, is just so the vectorial, math or addition or subtraction makes sense. And it does here, right? We have positive internal pressure, but then you end up with a net addition, and the final number is negative 74.3 PSF, which would be the controlling pressure here in this case. Now let's look at the negative internal pressure and see how that plays out. The negative internal pressure, now it's when we have positive exterior or external pressure paired with negative internal pressure, they add up, right? The two pressures. So if we see mathematically, we see that we have a controlling pressure of 58.4 PSF. And then the other one, it's not going to control. And we're gonna see that we got 53.1 PSF. So at the end of the day, we see that our controlling pressure out of all these cases is 74.3. Usually, people just do the two cases that they know the pressures are adding up, but technically we're supposed to do all 4 just so you see which one will always control. And there you have it. This is the concept of effective wind area. Like I said, if you want to get this example in a PDF format, I can email it directly to you and you join my weekly newsletter. If you enjoyed this video and you want to get more resources about wind loads and structural engineering in general, or just want to stay more up to date with all that I'm doing behind the scenes, make sure to join the newsletter in the link below. And I'll see you next time.